Okay, so for this section in Chapter 5, our new chapter, I'm going to do a quick little review on rectangular approximation methods. So first of all, let's just talk a little bit about area under the curve. Let's say we have a train that is traveling along the path modeled by this function v of t equals to t squared, where this represents the velocity of the train traveling along. The area under this curve, all of this would represent the total distance traveled. But the trouble with finding the area under this curvy section is, how are we going to do that? We're used to finding areas of rectangles. Those are easy, length times width. Okay, so since we have a function, v of t equals to t squared, let's just say I want to restrict this between 0 and 2. So just within the first 2 hours that the train has traveled, what would be the total distance traveled? Okay, so we're going to first experiment and take a look at this by doing what we call a left-hand approximation method. So we're going to break this from 0 to 2. This is going to be LRAM, or left-hand rectangular approximation method. Okay, so I want to have a subinterval that has a width of what we call delta x. If we're going to go from A to B, each of my subintervals would be whatever b minus a is, so 2 minus a, or 2 minus 0, divided by how many of those subintervals that we have. So if we have subinterval n, then the width is going to be delta x equals b minus a over n. So in this case, let's say I want to have 4 subintervals. So that means I would break each one of these up from 0 to 2 into 4 pieces. Well, what would the width of this be? Delta x equals 2 minus 0 over the number of rectangles or subintervals we want, which is 4. So therefore my width, delta x, is 1/2. And in the left-hand approximation method, what we want is to have the rectangles fitting over this particular width with its height determined by the function. So in this case, over here, the first rectangle will have a height of 0. The second rectangle will have a height of f of 1/2, which is 1/4. This coordinate point would be 1/2 comma 1/4. And then the next rectangle we have, its height would be determined by the y value at 1, which makes it 1, 1. And then our final and fourth rectangle, its height would be determined by its value at 3/2. So 3/2 comma 9/4. So if I write out the entire calculation, the first rectangle is kind of silly. It has a height of 0 and a width of 1/2. The second one, it had a height of f of 1/2, which was our 1/4, with a width of 1/2. The next one had a height of f of 1 times the width of 1/2. And then the last one was f of 3/2 times the width of 1/2. So I hope you can see that you have the 1/2 everywhere. There's 1/2 in every single one of these terms, because that's our width. So I could actually factor that out and leave myself with basically f of 0 plus f of 1/2 plus f of 1 plus f of 3/2. If you plug in all these numbers and add them up, should end up nicely and equal 14 over 8 with a common denominator. Okay, so that's the left-hand approximation method. Okay, now we'll also talk about RRAM, and it works really similar to this, except guess what? The right-hand side will be on our curve. So here's our y equals to x squared function again, going from 0 to 2. Now we're going to set it up in much the same way. I'm going to break it up into 4 subintervals so that the first width, which is from 0 to 1/2, will have a height of f of 1/2. So its height times the width is f of 1/2 times 1/2. Now the second rectangle, it's going to be at 1. So f of 1 will determine the height. So before I forget, let me write this in. 1/2, f of 1/2. Our next one is going to be 1 f of 1. F of 1 times 1/2. Our third one is going to have a height of f of 3/2. So that's 3/2, f of 3/2. And then our very last rectangle, it's going to be super tall. It's going to have a height of what? 4. So this is going to be 2 comma f of 2. Notice how this particular function, because it is concave up and increasing everywhere, all of the rectangles that I happen to draw lie on the outside of my region. And that's okay. All that means is that we are going to have an over approximation. If you go back and look at our LRAM rectangles, they were all underneath, and that's again only because it is increasing concave up. It would give us an under approximation. So sometimes one method gives you an over, sometimes one method gives you an under. And we can plug in all our numbers. I can actually also factor out the 1/2. So we'll be adding up 1/4. Now these are all the heights. 1/4 plus 1 plus 9/4 plus 4, which is going to end up with 30/8. And if you compare the two answers that we have so far, they're pretty different, 14/8 and 30/8. But again, that's because we have an over approximation and an under approximation. So the last one that we have is MRAM. That's going to stand for a midpoint rectangular approximation. So in this case, this one's a little bit trickier. For every subinterval that we have, so in this case, here's our first one, we are going to use the midpoint of that segment to determine its height. So this time I'm going to actually draw it in for each one of these first. When you have the midpoint approximation method, some of the parts of the rectangle are inside or underneath, and parts of it are outside or over it. So I hope you can tell that it's, a seemingly better approximation because it gets a little bit closer, a little bit over, a little bit under. It is a little bit trickier to write out, so let's see what this looks like. This first one is going to be in between 0 and 1/2, so that means f of 1/4 times the width, which is 1/2. Remember, the width is always the same. Then on our next one, it's going to be in between 1/2 and 1, so that's f of 3/4 times our width 1/2. And then our next one, between 1 and 3/2, so that's f of 5/4 times its width. And the last one is f of 7/4 times its width. Writing all of these out, this would be 1/2 times 1/16 plus 9/16 plus 25/16 plus 49/16, 84/2 times 16, which we can reduce by dividing 4 out and leaving ourselves with 21/8. If you guys have your calculators, I believe I gave you guys a program on there called RSum, Riemann sum. And if you don't have that one, you can go ahead and use INGRL, which is integral. But I'm going to go ahead and use RSum today. So we'll run the program. Oh, wait, sorry, back up. Let's make sure you have your function entered in under y1. So I want to just show you what it looks like with the equation that we did earlier. The function for the velocity of that train, so y equals to x squared. So then we'll go back to our program, which we're going to run by hitting enter. And it's going to ask us for the left endpoint. So we're going to go from 0, hit enter, right endpoint to 2, and enter again. You're being asked the number of intervals, which in this case was 4, so you do have to know that. And it's asking us which case we want to do. Do we want the left-hand case, so LRAM? Do we want RRAM? Do we want MRAM, or a random one? We're going to go ahead and choose LRAM. So there is my graph, y equals to x squared. Now if your window doesn't quite look like mine, that's because you need to adjust your window before you start. Adjust your x-axis and your y-axis scale to whatever you'd like it to be. Now, you're not really going to be able to get anywhere at this point, because if you see the little 4 scrolling dots, that means your calculator is working. So we have to continue by hitting enter, and it tells us the sum is 1.75. And if you compare that number to what we had calculated, 14 over 8, that would be 1.75. Now notice it's still waiting, it's still processing over here on the right hand side, so I'm going to hit enter one more time. We can either choose a new type, a new n, or quit. So I'm going to go ahead and choose a new type for now, and I'm going to choose the right hand approximation method. And notice it puts our rectangles over our parabola because it's increasing concave up, and you can see right here where the right hand portion of our rectangle lies on our curve. So I hope you guys get the idea. And if you would like to change your n value, you type in new n, and let's just do 8. And we'll do midpoint this time. See how that looks. Oh, it's a little bit hard to see. If you change your y-axis scale a little bit, it might look better. And you can see how it fits over the midpoint of the section. Now, you'll have to quit, so hit 3. And I guess just really quickly, let's just run integral just in case. Notice it's very similar. You have to have the function already entered in. And notice it says use input first. You must run this before you start working on left, midpoint, right. This is a different program set up a little bit differently. So it'll ask you for left endpoint. This time, let's do 4 to be a little different. And let's say 8 subintervals. So we have to do that setup first. Then you just choose left. See, and in this case, it's a little bit different. You don't quite see the graph. The approximate answer is what it's approximately equal to. This exact right here is exactly what it is if you used an integral with an error calculation of negative 3.83333, and it reminds you that n equals to 8 on this problem. Okay, so notice how it's a little bit different.